Hello, welcome back. I hope you can hear us out there.
Hello, hello.
So, where are we now? What's going on? So, Simo, can you let us know what's upcoming?
Yeah, so we had great talks in the morning with Susan and Jarno and you, and now we are jumping back to where we left off yesterday. So yesterday we were writing stuff, we were running stuff in the queue, like we were testing stuff in the queue, and we were testing out the the submission scripts. So we were trying out how we can write scripts that can be run in the queue. So they can be run like we can submit them to the queue, and the queue will run them later on. So that was the thing that we were doing yesterday, and now we are going to get further in our users of the cluster, because we don't only want to do one thing. Usually we want to do a lot of things. So that's why we want to make it so that we can run a lot of stuff. So that involves parallelism, and the parallel is like the whole thing about this day. So we'll first talk about a bit about different ways of doing stuff in parallel in cluster, because we have a lot of computers in the cluster, and we want to use as much as we can to get all of our stuff done. And we'll talk about the different ways you can do it, and then we'll tackle 3 of those 4 ways today.
Mm-hmm.
So we'll talk about array jobs, then we'll talk about a shared memory parallelism, and then MPI jobs. And that's about it.
Yeah.
And we'll do some exercises on those.
Okay, great. So I guess I'll switch to my screen. And it worked. So what now? Where do we start?
So let's first look at, if you want to show the serial jobs, what we were doing previously. Let's look at a diagram that might refresh us. So previously we were writing these scripts, and we were doing also interactive runs, where we were running something in the compute nodes, and we were currently using only one computer, only one processor. And these are called serial jobs, because they they do the commands in order.
Serial.
They run like
So
a
like the
series
opposite of parallel.
commands.
So
Yeah, like we write one script, and then we execute that in the cluster, and it executes everything in order, like it does everything, and it uses one CPU currently. So we're taking only a small slice of the whole cluster. Like we are taking one CPU in one node, and the whole cluster is a big thing. So we want to use more. And the first and the easiest way of doing is usually to split up your job, what you're basically doing, split up what you're doing, and do an array job. So maybe we could talk about the different parallelism modes, and let's we could maybe show a picture of an array job.
Yeah, so I'm opening this, the parallel one from the schedule. I guess we're looking at these things. So let's go down. This is an array job. So what's the characteristic here?
So the idea behind an array job is basically like, let's say you have a script that describes what you want to do, but you want to do it like with multiple data sets, or you want to do it with multiple different like random numbers, or you want to do it with different or like options, different startup options. You want to have different parameters for your model or something. But they're basically the same thing, but there's something that changes.
Yeah.
And you want to do it the same thing.
Yeah. So we take the big problem, you make it a bunch of small problems, and each small problem is only slightly different. And you can basically load up every small available place on the cluster.
Yeah, you get like independent jobs, and it's often called like embarrassingly parallel, not because it's not embarrassing to use it, but it's because it's so easy to parallelize. Like basically like previously we had the HPC kitchen metaphor, And we talked about like CPUs being like stovetop burners. So if you put two kettles in two different burners, they're independent of each other. They're not like interacting, but you can like cook more like two pasta varieties in different pots, and like they work independently of each other in independent burners. So this is basically the idea. So the array jobs are spread out throughout the cluster. There's this nice syntax that you can use to easily create like even a large array job of, let's say, 100 jobs running at the same time, and each of them works independently.
Okay, so we're not doing it now, but should we preview the things we'll do is at the end of the day?
Yes. So the other methods that we're going to be talking about are like a bit more involved. And the first one of these is like shared memory parallelism. And this is like basically what your laptop is doing right now, or your computer. Like you have multiple processors in your computer, and you can, but it's all inside this one computer, right? Like you don't have other computer there like connected to that. You only have one computer, but it has multiple processors. So you can, if you have a problem that where it suits the problem, you can use multiple processors in the same machine to calculate something faster. So this is like this just usually makes calculations faster if your program supports it.
Yeah. Okay, and I guess this is relatively easy to do.
Yeah, so your job ends up in one of the computers, and then like you can have multiple processors working together to solve a bigger problem. And this is like it's of course limited by the size of the computer that you're going to be using or getting, but this is something that we'll be talking in more detail later on.
Yeah. Okay. And finally, we have the shared or
we have MPI jobs.
What's it called? Message passing.
Yeah, so message passing jobs. So this is like the traditional high performance computing, like supercomputing. If you think about like big weather models or whatever, they often use or most often use this message passing interface, which is like this standard that has been created since the 90s or something like that makes it possible for a lot of different processors in different computers to know about each other and talk with each other to solve a really big problem. So you can utilize multiple computers at the same time, and you need to you can like each of these can communicate with each other. But this is a bit more involved, and it's specific for programs that use this. So we'll talk about this later. But nowadays, I think vast majority of problems are array jobs, or like vast majority of parallelism is nowadays array jobs or shared memory. But in the big clusters, the MPI is still a very big thing.
Right. Yeah. Okay. So should we get started with array jobs then?
Yeah.
So I'll close this window and let's open array jobs.
Yes. So when we're going to be demoing a few of the like array jobs, and we're going to contrast them with the serial job that we did yesterday. So if you didn't manage to do it yesterday, or if you weren't here, there's instructions in the notes on how you can bring yourself up to speed. So basically how you can download the example dataset and the examples repository, and there's an example like solution script for the serial job script, so that we can like then compare the results.
Yeah. Okay. So since I didn't do the typing yesterday, I've set up where I've logged into the cluster and I've copied the data to my personal work directory in a Gutenberg fiction folder, just like before. So hopefully it will be pretty similar to what we did yesterday. We're in a fairly similar place. Yeah, so I guess the first thing I'll do when I've logged in, I want to see where we are. So I type pwd, and I'm in my home directory. And I know I need to go to the same place I was yesterday, which is the HPC examples directory. So I'll change there.
Yeah, it's always a good idea to go to the work directory whenever you go to the cluster.
Yeah. And verify where you are before you start running commands.
Yeah.
It's a small but important thing. Okay,
Yeah.
so here we are.
So
yeah.
Do you have the previous script there? The previous.
No, maybe let's go over making it again.
Yeah, we
I
can
can copy it from the notes here if you'd like.
Yeah, let's do that.
So nano, what was it called? Count
ngrams
2.sh.
Yes.
And I'll just put it in this directory, I guess. So
yes.
Do you want to remind us what these things are as I type them?
Yes. So there's the first line is the shebang, or that tells which, like, it's the magic that runs everything with the terminal. I think our pictures are a bit cutting off the terminal.
Shrink that down some.
Yes. And then we need to tell the queue system what were the requirements that what memory we want, what time we want, and then we need to tell what we want to actually run. So in this case, it was the ngrams. We took the 2 grams, so every 2-word pair, and we wanted to get those calculated, and we gave it the folder of the the folder of where we had the data set downloaded and the path to the data set that we wanted to analyze. And you can use Richard is using this backslash syntax. So if you put as the last character, you put this backslash, you can continue from the next line. So basically, like, it means that, like, just continue, combine these together so that you can fit more stuff into the
and make sure it's the very last line.
Yeah.
Should I run this just to make sure that it actually works?
Yeah,
so
let's do that.
Control X to exit, Y, yes.
Yeah. So now Richard is checking that it's in the queue. So it is running. It's the last one over there.
Yeah.
So it is running, and then it's probably finishes quite quickly. Yeah, it takes a minute to run. But now the question is that, okay, like, this is quite a simple program, but let's imagine that our data would be a lot bigger. So let's imagine that we would have a lot bigger of a data set. So in that case, we might want to do these calculations of these n-grams for like, we would want to do it in pieces, right? Like, we don't necessarily want to have one job that does everything. We could do it so that, like, every job, like, we could split it up the program so that we could split it up to, let's say, 10 programs, that each program would do 1/10 of the analysis.
Yeah. So are you roughly saying we have 100 books in this sample data? So we'll have one program do 10 books, the next do 10 more books, and so on. We can run 10 things at the same time. And then I guess that means we get 10 different output files.
Yes.
That have to be combined. But it can, in theory, run 10 times as fast.
Yes, and that was very, very well put. So, and for this, we can use, like, the program, the ngrams program. It supports these start and step functions. So you can decide, you can tell it that, hey, I want you to take every 10th book. I want you to start from a certain number. So we can modify the count ngrams 2 code. So if we make a copy of it into, let's call it an array, count ngrams, and not the output, but the count ngram.
sh. So
count.
this does look good. Yeah. Wait. Yeah.
Yes. So let's modify the code a bit, and let's try to like split it up the work to multiple workers. So if you look at now the array script.
Yeah, okay.
So we can do
So how
small
do I
additions
modify
here.
this?
Yeah. So we can do small additions here that make it so that like we can split it up. So the first important thing about the array thing is that when you want to submit an array job, you add this s batch and then -- array, and then let's say it's from 0 to 9. And what this syntax, this looks a bit interesting, but what this syntax tells the queue system, like the queue system will read this comment and it will recognize that, hey, the user wants me to create 10 copies basically from 0 to 9, right? And it wants me to create 10 copies of the same job. All of those jobs are independent and all of those get the same requirements. So it's not like additive. You don't get like 10 gigabytes, so you don't need to modify the requirements in a way. Of course, like in this case, like some of like if we split up a big program, each of those might have less requirements to do, but that's not necessarily something we need to think about.
Not thinking about that now. Okay,
but so basically we're running 10 identical copies here. But if we don't do any modifications to the running part of the code, now like the Python call, we are going to be running the same thing 10 times, and that's no fun. Like we will get
waste.
Yeah, that's
Hopefully
a waste of resources.
Exactly the same 10 times.
Yes. But instead of what we can do is we can like this program supports a different starting point. So we can use a different starting point for like which book we want to analyze. So if we add here --start and then we put there a magical environment variable. So in terminal you can have these environment variables that are like something that will be filled later. It's just a variable that will be filled later. And for the array, it's called Slurm array task ID with underscores and all capital letters. So it's very important that it's written correctly.
Exactly like this, I guess.
Yeah, exactly like that. But once you have written it like out loud, like a few times, you will remember it, and it will be it will become more natural. And what this
like for me, even every time I do that, I almost always look at a reference just to make sure I'm spelling it right. So don't be afraid there. Okay, so this means it starts and Slurm array task ID becomes the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, I guess.
Yes. Because so what the So when we submit the array job, we will get an like a number for each of these array tasks. So we get a number. So the number, well, that's the task ID running based on what are the numbers we are giving in the array, like line over there, the S-batch array. And each of them gets a different one. So what we do with those numbers is up to us. And that's the beauty and the complexity of the array jobs, that we can map this number to any sort of like parameter values. We can map it into data sets. You can do whatever you want with this number, as long as you map it to something different for each job. There's many examples in the array jobs tutorial page of different kinds of structures you can use to map this into different things.
Yeah. And I guess if the program didn't support the start option, it wouldn't be easy to do this with arrays. You'd have to somehow add it yourself.
Yes, quite often you want to implement this sort of functionality in your code. Like if you know that you are planning on using the code for, let's say, running at 100 different things, you might want to implement in your code functionality where it can take a number and based on that number do something different.
Yeah. But so is there anything else we need to do for this then?
So we need to, like, currently we are setting up a starting point, but we are not setting up a stepping stride. So if we would only have the starting point, we would, like, everyone would start at a different number, but then they would analyze all of the rest as normal. So we need to set this step over here to be 10, so that, like, everyone takes, or in every 10th book. So 0, like Rich is writing, we get numbers like that, and then 1, 11.
1, 11, 21.
Yeah. And so forth.
91, I guess.
Yes.
And this, so when we made this program, this is basically like the Python array slicing. So you give a start and a step. And I think you could also give a stop there. So it's, well, if you know the Python syntax, it looks familiar. If not, well, then it doesn't really matter.
And like but we could try out submitting this and see what happens.
Should we adjust the output? Because
that's
like
a great
point.
Yes, great point. I almost forgot. So like, if we wouldn't change the output, everyone would be writing into the same file. So instead, let's call it ngrams2 and then dash array and then underscore Slurm array task ID. So now, yes. So now, like, because all of these programs will run independently, all of them need to have an independent output as well. So yes, we want them to write to different files. And again, like, the Slurm array task ID will be filled when the code is actually running. So it's based on the array number that it gets. So now I think we are ready.
Okay. Yeah, so I exit and save. Do we trust it works?
I think it's going to be fine.
It looks good to me, so let's hope. So count sbatch count ngrams array2.sh.
And if you now look the queue, what does this queue say? So, we see, we see that we have now this very weird job ID for the job. So what that means is that
quickly.
Maybe you can try running it again and trying it again with the scheme. But this structure means that we get, like, the same job, but with like basically 10 copies of it, and it will like, we have only one ID for the whole, like, average of, and this makes it easier for the queue system to also understand, like, okay, now we have, like, the same thing but 10 times, and now we see like how it looks actually in the queue. So once the resources are
running,
once the resources are reserved, we get these array jobs running, and
0, 1, 2,
each one gets a different ID, and you notice that some of them are running in completely different machines, or most of them are running in completely different machines, because they are independent, right? Like, all of these are independent, and they will be running independently of each other. So let's look at the output. Did it crash, or did we get anything in the output files?
Oh, there's a lot of output. Oh, I see this output is doubled here. Should we look at what should we look at?
Let's look at the ngrams output first. Let's verify that it worked correctly. So we get a lot of output over here.
Editor.
Yeah.
And it's
and it looks
7,000. So that's about 1/10 of what was there before, I think. Should we look at number 1?
Sure.
Yeah, okay.
Yeah, so what we get is we get independent outputs from all of these, but we also get these Slurm outputs as well. And by default, when you have this array structure, you have you have this the Slurm. It's called Slurm, and then you have the job ID and the array task ID after that, and it captures all of the output from each array job. So let's say you have you need to do some analysis 100 times, and each one takes an hour or something, and then one of them crashes. You can look at the outputs and see that, okay, that one crashed. What was the problem with that one? And then you can figure out that, okay, maybe there's a corrupted data or something. But each one is independent, and each one gets an independent output.
Yeah. Maybe we should almost go to an exercise.
Yes.
Is there anything
let's
else
look at one of the outputs, and let's then check the combined data. What did we actually get what we wanted? So if we look at one of the Slurm outputs,
the output of 0. It says it found the 100 files. It didn't say which files it's processing.
Yeah.
But
yes. But it looks like it ran in about 3 seconds. So each of these was very fast because now we're splitting it into 10 parts.
Yeah.
But let's try combining the data together.
How do we do that?
So we do it by running
combine counts.
Yes.
I'll run help first and let's see what it says.
Yes. So it needs the output count files, and then it has an output file.
Yeah. Python combine files.
And don't worry, we'll post all of the commands that we're going to be running into the notes in a second, so that you can try them out in the exercise.
So I guess this is how I'll run it. Python 3, the program name, and I can use an asterisk to glob and capture everything that starts with this, which I know will be the 10 files that are needed.
Yes, and then you specify the output
somewhere.
Yeah, you have the out and the n-grams. Yeah, to array out. That looks good. Dot out.
Yeah. Okay. Dot out.
Takes a while to combine them.
Yeah.
So this is this kind of this is the kind of a map reduce kind of a situation where we map the same functionality onto different data, and then we reduce the results into together. So if we look at the output,
take a look. Should we see if it looks the same as the non-array
so
one?
62,000
numbers. 623, and if we do array n-grams 2 dot out, exactly the same, at least the first number.
So this is a bit of a toy example, but if we would have, let's say, the data would be a lot bigger, then this would be really speed up the execution. And
to use a neuroimaging example, if we have 100 brain images to process and they each take a few hours to do, we can do them in parallel, even 100 times in parallel. Okay.
And now let's go to exercises. So the exercises, we'll post the commands that we just run into the notes, and you can create your own array script, or you can already start writing it if you feel like doing that. And after that, we in the array examples, there are very many examples. They use this pi example, but there's many examples of different ways you can choose the different you can use different array IDs in different ways. And if you have more time, check out a few of those and run a few of those examples and see what they do. But let's go to the exercises. And should we have about 20 minutes?
Guess that will start getting into the lunchtime a little bit.
Okay.
I guess we can
15.
Go some people, or should we just combine the exercises with lunchtime? And then people can beat the queues of the places or whatever.
Maybe
if there's
we'll have 50 minutes of exercise, and then we'll talk about a few of the questions, and then we'll return to it after lunch.
Okay.
Later.
So at 40, no, 50.
Well, yeah. 50, let's go 55.
55, yeah.
Yeah.
And
then
you can try some ask questions, and there's more time during the lunch break. So yeah. Okay.
Yeah.
And the task of people will be to do basically what we've done here.
Yeah.
Is that the case? Okay.
Yes.
And I think Sima will be pasting in commands and more detailed instructions to the notes. Okay, great.
Yeah.
So see you in about 11 or 12 minutes. Okay, bye.
Yep. Bye.
Hello, we are back. So our plan now, I believe, is to go over some of the questions and stuff, and then we go to the lunch break and we can do one more array example after lunch. So which questions were most relevant here? There's some on best practices, like, oh yes, please, even for a reference or a future, please let us know if you did the exercise, weren't trying, or had some problems, because this will help us plan for future years. So yeah, so this is a good question here. So if someone goes and makes an array job, like you run 1 million array jobs that each take 10 seconds, that's not a very good thing, because it's a lot of scheduling overhead to constantly be finding these spaces, planning it, running it, stopping it, and restarting it. So that's sort of an extreme example, but what's our rule of thumb? Try to make the jobs at least 15 minutes, but if
Yeah,
it
like
can be
usually we
longer,
talk about half an hour
better.
or an hour is better. But like, yeah, like it depends how in a hurry are you. Like if you want to get most done, you usually want it to be, let's say, an hour. If you want the results now, less than 15 minutes is fine. But if you do, like, let's say 100 jobs less than 15 minutes, that's going to, like, at some point somebody will send you a mail of like why like this, because it's not good for the queue. Like the queue system doesn't like if there's like huge number of jobs happening that are very small. Like it doesn't usually like that. And there was also a question in the chat, like why not just use like a bash script that submits jobs or something like that. And the reason behind that is like the array structure is much more better handled by the queue. Like it's been designed for this sort of workflow. Like if you have a bash script that just submits stuff, then like each of these are independent, and the queue cannot like reuse the same information it gets from all of the array jobs. So it's not as good. So please use the array structure instead. And the good benefit with the array structure is that it's reproducible, because like you then know what is the mapping between the array indices and the different things, and it's very easy to then look at it later on and see that, okay, I run it with these array indices, so I get these results. And there was also a question,
if one of them fails, they don't all fail or something.
Yeah.
You can run
There's also questions of more complex parameters. So after the lunch, we'll talk about like an example of how you can map out different kind of like combinations of parameters. If you have like multiple parameters you want to do, like you can use array to map to those. Like you can map one number to multiple things. That's possible. And if you have a situation where you have very small things that you need to do a lot, what you can do is that you can have an array job where inside each job you have like a for loop that does like 10 things or 20 things. Like if you have something that only takes 10 seconds, but you need to do it like 100,000 times, like you can split it up so that you have like, let's say 10,000 or 1,000 10-second things running in like each array job. And then like you can you can call it, like set up what is the runtime, basically how many iterations you want inside one job. But usually it's this kind of like, okay, you can think of it a bit like you can have either like a really thin rectangle with the same surface area as like a very wide one, and like like as long as you keep the number of like things that are needed to be done the same, you can rearrange it in a way that like you can do it in like you can do small number of jobs that do a lot of things, or you can have a large number of jobs that do few things. So
so I guess most of the people asking these questions, like, can I do X with array jobs? The answer is always yes, if you write the code, whether it's in Python or Shell or whatever else, to do the splitting up, and if it doesn't make it too short. And this is why we have other courses on shell scripting and stuff like that. Knowing a little bit of Bash can save you a lot of time doing other stuff.
So, and if you have problems like figuring out, okay, like does my program, can I split it up? How do I split it up? What would be the best way? Like, again, asking for help is a good thing, because like for different projects, like you might have a different thing you want to split it up by, and like all tasks are individual. So it depends on the task at hand. How do you want to split it up? But
anyway,
maybe we should
I guess it's lunchtime. So should we head there? See you in an hour.
Yeah, and then when we come back, we'll talk a bit more about arrays, about more complex array things, and then we'll jump into applications and other things in the cluster, monitoring jobs and that sort of stuff.
So array example and some more philosophical stuff before parallel. Okay.
Yeah.
Great. And as always, you can keep asking questions. So talk to you later then. Bye. Hello. Are we back? I think so. I hope you had a good lunch break. I think we did here. So what comes next? So my understanding, we have another quick demo of array jobs, and we talk about monitoring and applications. Any other notes and stuff to review from, or questions from the notes to review?
I think
seems
there's plenty of good discussion there, and I recommend reading up on it later on if you feel like it. But I think we can move forwards, and let's go, like many of the topics in there touched the subject of, okay, what can you do with the array jobs, and let's look at one of the more like complex examples, and let's run one of these from the examples in the course material. So Richard, if you want to run the case example.
Yes. So okay, let me
it
find
is in the
first.
Yes.
So what do I type? So this is a new thing. This is with pi, calculating pi.
So in the parallel part, when we are going to switch into another example, which is much more like computational example, and it was already mentioned in the beginning of the day, and it's a bit of a toy example where it calculates or estimates the number of pi using a stochastic test. So basically, it's like throwing dart at a dartboard, and whether it hits the dartboard, it will like calculate how many hits do you get, and I estimate pi by that. So it's a very like a toy model, but it's very easy to parallelize for multiple CPUs and stuff like that, or relatively easy to optimize for that. So
and here I see we have five array tasks: 0, 1, 2, 3, 4, 5.
Yes, and the for that we want to like test out a different kind of way of of spreading, like, or choosing the parameters. In this case, we might want to choose a seed number for the like the random process that we're going to be doing. So we can decide which number we want to use. And in Bash, it's a whole like programming language, the terminal. So you can do, for example, this case statement that Richard has written. So basically, based on the number of the Slurm array, it's mistyped actually. So
yes.
based on the number in the Slurm array task ID, a different value will be set to this variable seed. So let's say you want to like test different parameters out. It's very easy to test it with this this kind of like a syntax. Like then there's more complex syntax that you can use in the other examples. You can take the parameters from a file, or you can do all sorts of things. But this is like very easy way of testing out. So over here we try.
So I guess there's the seed.
Yeah. Yes, and we try out the what we get from the Slurm Pi. And you notice also in the SBATS statement, we have changed the output file name of where the output of the up in the top, like in the SBATS statements, we have changed the output file name, and you can use these wildcards. They are documented in the documentation sections. Like you can use this %a to denote the Slurm array task ID. So if you want to like create your own output file for the Slurm output, then you can like use this sort of a syntax for that. But let's
I guess everything's configurable.
Yeah.
Okay.
So what this will do is that it will do 2.5 million iterations with different seed values, and it will print out the outputs into pi underscore and the seed number, and then it will like print out the Slurm outputs into the pi array hard-coded with the array index. So let's try it out.
Okay. Exit, save, yes.
And there's, like I said, there's multiple of these different things that different ways that you can do this array kind of like expansion. So
yes, first I make sure I'm where I expect to be after the break. Pi array.sh. If we do slurm q, it's already running. So 4 things, and it's done.
If you want to look at one of the outputs and
okay, now this is a lot of files here.
Yeah.
So what are the new ones?
The pi array hard-coded.
These are the output files.
Yeah.
Should we look at the first one?
Yeah. So this is the output that the code, what the code runs. But the actual output of the code is going into the pi underscore and then
pi 1, 2, 3. Okay, and it's JSON structure that says stuff. So I guess this is a way where if you have different file names that aren't predictably named, you can sort of hard code like what the inputs are or what the hyperparameters are or whatever like that.
Yeah, and there's a lot of flexibility in the array jobs for this.
Yeah.
But okay, I think you probably get the idea that you can you can check this out later. We'll check out the different examples. So maybe we should jump into the next section, which is about